good afternoon friends. Welcome to CEC EduSet live lecture. Dear friends, for you we are going to conduct series of lectures on stereochemistry of organic compound, and under this very topic we are going to discuss today constitutional and geometrical isomerism. And for this we have with us in our studios Dr. K.K. Arora. He is Associate Professor in Zakir Hussain Delhi College, University of Delhi. So first of all, I would like to welcome our guest Dr. K.K. Arora, and through him we are going to learn what basically isomerism is and what is constitutional and geometrical isomerism. So first of all, I would like to welcome our guest Dr. K.K. Arora. Sir, welcome to the EduSet lecture. As we are going to conduct series of lectures on stereochemistry of organic compounds, and we are going to start from a very beginning, that is we are going to learn about what isomerism basically is. So sir, over to you.
Thank you. Hello viewers, welcome to this series of lectures on stereochemistry of organic compounds. Now first let us talk about what do you mean by the term stereochemistry. Actually it is a branch in chemistry which deals with the three-dimensional structures of organic molecules. In this we discuss the three-dimensional structure of the molecules as well as the changes that occur during a chemical reaction. Stereo, it's a Greek word which means solid. Solid signifies here three dimensions basically, or space. So we talk about the structure of molecules in three dimension or the spatial arrangement of molecules. So we will take up these things in detail in series of lectures. There are two aspects of stereochemistry. One is, we call it as a stereoisomerism, and another is the structural changes are three-dimensional changes in molecules during a chemical reactions. Our today's lecture has been outlined like this, that we will be taking up first definition and aspects of stereochemistry, about which briefly I have already talked. Then we will take up isomerism and its classification. We will talk about constitutional isomerism and its types. Then we will take up the stereoisomerism, and one of the important type of stereoisomerism is geometrical isomerism, which we will discuss in detail today. And then we will take that what type of compounds can show geometrical isomerism. They may have carbon-carbon double bond, or they may be without carbon-carbon double bond, that is they may be cyclic compounds with carbon-carbon single bonds, or there may be some other elements in absence of carbon. And finally we will summarize our today's work. Now stereochemistry, as I told you, it is the branch that involves the study of arrangement of atoms of a molecule in three dimension. It is also known as 3D chemistry. And one important aspect of stereochemistry is the changes that occur in spatial arrangement of atoms during a reaction. And another important aspect of stereochemistry is stereoisomerism. But before going into stereoisomerism, let's talk about what is isomerism. Isomerism itself consists of two words, isos and meros. Isos means equal and meros means parts, means something which is made up of equal parts, and in terms of our molecules means they have equal number of identical atoms. So the compounds which have same number of identical atoms, in other words we will say that they have the same molecular formula, they show some difference, so that become different compounds. This phenomena is called isomerism. So we can define like this, that existence of two or more compounds with the same molecular formula but different properties. Such compounds are called isomers. Isomers may have different physical properties, different chemical properties, or both, but they will definitely show some difference in their properties. Now isomerism itself can be classified into two types. One we call as a constitutional isomerism. The another name that was used earlier for constitutional isomerism is structural isomerism. Constitutional word means they differ in their constitution, means there is difference in their bond connectivity. How the atoms are attached to each other, that connectivity is different. Such compounds are classified as constitutional isomers. And second is stereoisomerism. Stereoisomers, they differ only in the arrangement of atoms in space, but the connectivity of the atoms, that is which atom is connected to which other atom in the molecule, that remains same. So before moving on to stereoisomerism, let's briefly talk about constitutional isomerism. Constitutional isomerism is defined like this, that it refers to the existence of different compounds having the same molecular formula, but different sequence in which their atoms are bonded, or in other words we say in their connectivity. Constitutional isomerism is of 6 types basically. They are chain isomerism, positional isomerism, functional isomerism, metamerism, tautomerism and ring chain isomerism. The first 3 types, that is chain, position and functional, these are the 3 basic types of isomerism. Whereas metamerism, tautomerism and ring chain isomerism, they are the special cases. Metamerism is the special case of positional isomerism, tautomerism is the special case of functional isomerism, whereas the ring chain isomerism is a special case in chain isomerism. Briefly we will take up these types of isomerism with the help of some examples. Chain isomerism. Existence of 2 or more compounds having similar molecular formula but different carbon skeleton, means the way the carbon atoms in the molecule are attached to each other, they form different types of chains. Such as this is a molecule of 4 carbon atoms, basically I will call it as butane. But these 4 carbon atoms can be joined to each other in the sequence as shown, and we can show with the help of molecule picture like this. That is the first structure. The 4 carbons are attached in a sequence 1, 2, 3 and 4. Whereas in the second structure we find that there is a chain of 3 carbons 1, 2 and then 3, and the 4th carbon is attached to the carbon number 2. These are 2 different compounds, and when we name them according to IUPAC system, the first compound is called butane and the second compound is called 2-methyl butane. Now the 2 compounds have same molecular formula, but they differ in the type of chains, hence they are classified as chain isomers. Let us take another example. This is a 5 carbon compound, pentane. The 5 carbons may be attached to each other as shown in this model, or they can be attached like this, that there is a chain of 4 carbon and then 1 carbon is present as a substituent. This compound is named as 2-methyl butane, or there is a possibility that there is a chain of 3 carbons 1, 2 and 3, and there are 2 carbons, one here and one here. They are attached as side chain at carbon number 2. This compound is called 2,2-dimethyl propane. Now again all these 3 compounds have same molecular formula, but they differ in the chain length. One has length of 5 carbon chain, another is a 4 carbon chain, third is a 3 carbon chain. So these isomers are classified as chain isomers. Next we take up another type of isomerism, position isomerism. Position isomers are the compounds which have any substituent or the functional group present at different position on the same chain. Let us see in this example. This is an alcohol of 3 carbon. OH group is attached to carbon number 1 here, and this is called 1-propanol. This is a molecule picture. 3 carbons are attached in the chain and then 1 hydroxyl attached to carbon number 1. Then there can be another molecule with the same molecular formula, where again we have the chain of 3 carbons, but the hydroxyl group is attached to carbon number 2 here. This compound is called 2-propanol. Now where these 2 compounds differ? They differ in the position of hydroxyl group on the same chain. In the first case, hydroxyl is present at carbon number 1, and in second the hydroxyl group is present at carbon number 2. So, such compounds are classified as position isomers. Let us take another example. This is a 4 carbon alkene, whereas a double bond is present in this molecule between carbon number 1 and carbon number 2. This is named as but1-ene. Then another compound is again 4 carbon compound, but the double bond is present between carbon number 2 and 3. It is named as but2-ene. So, where do these compounds differ? Both have a chain of 4 carbons, 1, 2, 3 and 4, and this compound also has chain of 4 carbons, 1, 2, 3 and then 4. They differ only in the position of the double bond. In first compound it is present between carbon number 1 and 2, and in second it is present between carbon number 2 and 3. So, they are also classified as position isomers. Next we take up functional isomers. Functional isomers are the compounds which have the same molecular formula, but they have different functional group. Such as this is a 3 carbon compound having a carbonyl group which is present as an aldehyde, and this compound is propanol, CH3, CH2 and then this C double bond OH. This is a 3 carbon compound having aldehydic functional group and named as propanol. Now, we have another 3 carbon compound. Here also the functional group is carbonyl group, but this carbonyl group is present at carbon number 2, and this is a ketone. This compound is named as propanone. So, these 2 compounds have again the same molecular formula, but they have different functional group. This is aldehyde, this is a ketone. So, these compounds are classified as functional isomer. Let us take another example for functional isomers. This compound has hydroxyl group attached to 2 carbon chain and it is named as ethanol. This is hydroxyl group. Then there can be another compound with 2 carbons and both of them are attached to oxygen. Here oxygen, 1 carbon is here and 1 carbon is on this side. This carbon is in the form of methyl group, here also it is in the form of a methyl group, and this compound is an ether. This is named as methoxymethane. So, these 2 compounds again have the same molecular formula, but they have entirely different set of properties because they have different functional groups. This is an alcohol, whereas this is an ether. Now, let us come to special cases. As I told you, metamerism is the special case of positional isomerism, and this arises when the functional group is such that it comes in between the carbon chain, that is, it breaks the continuity of carbon chain, and when it breaks the continuity at different position, the isomers result. Such as this compound, this is an ether of 4 carbon, oxygen is present after 2 carbons, means it is a 2 carbon portion ethyl group on this side and then ethyl group on this side. This is named as ethoxyethane. Another compound, this also an ether of 4 carbons, but it has a 3 carbon chain on one side and 1 carbon chain on another side. So, both the molecules have same molecular formula, same functional group, but functional group is breaking the continuity of carbon chain at 2 different places and they get different name. This is called ethoxyethane, whereas this is 1-methoxypropane. So, these type of isomers are classified as metamers. There is another example of metamerism in esters. This is an ester which is having an ethyl substituent on a 2 carbon acid, that is an acetic acid, and this is ester named as ethyl ethanoate, whereas this is a 3 carbon acid portion with methyl coming from alcohol, and this is named as methyl propanoate. So, both have the same molecular formula, both are 4 carbon compounds, but this oxygen of the ester is breaking the carbon chain as 2 and 2 carbon fractions, whereas in this it is a 3 carbon and 1 carbon fractions. So, they are also classified as metamers. They have the same functional group, same molecular formula. Then we come on to tautomerism. Tautomerism is the special case of functional isomerism, and in this case the functional groups are interchangeable by the movement of one hydrogen atom. Such a hydrogen atom is called as labile hydrogen atom. The name of the tautomerism is further specified by writing the names of the two functional groups, because there can be different functional groups which can be formed by the movement of this hydrogen atom. So, these tautomers are further grouped depending upon the functional groups which are being formed there. Such as, this is an example in which the starting compound is a ketone. Now, what happens if on this next carbon to the carbonyl group, this hydrogen, this is actually a labile hydrogen, it leaves and this pair of electron moves to form a bond here, and then pi electrons they move to oxygen and this hydrogen goes to this oxygen and we get OH group here. Now, this compound has got OH group, that is alcohol group, and a double bond. Double bond means ene and OH means all. So, this type of compounds are called as enol, and this is keto. So, one compound has a keto functional group, other compound has a enol functional group. This type of tautomerism is called as keto-enol tautomerism. In tautomerism, these compounds they remain in equilibrium. One can be converted into this, or this can be converted into this, but their ratio depends on many factors. It depends upon the solvent in which they are present, temperature, pH of the system, or even the overall stability of the molecule. It does not mean that if under one set of conditions a keto form of compound is more stable, it is not necessary that for all compounds the keto form be more stable. In some cases even the enol form may be more stable, because some other structural factors may lead to difference in their stability, like hydrogen bonding, etc. Let us take another example. This is an amide functional group. Now, in amides also this type of change is possible, that this hydrogen leaves from the nitrogen and it goes to this oxygen and we get this functional group. Now, this C double bond N OH, C double bond in imine and OH is all. So, this functional group is called as iminol, and this tautomerism is classified as amide iminol tautomerism. Another functional group can be this one, C double bond and OH, this is oxime. Oximes are obtained from aldehydes and ketones, and when this one H from oxygen leaves here and goes to this carbon and double bond shifts between nitrogen and oxygen, this is nitroso functional group. So, these compounds are classified as oxime nitroso, and tautomerism is called as oxime nitroso tautomerism. So, in case of tautomerism, the complete name for that type of tautomerism will be by naming the two functional groups which are in equilibrium with each other. Now, how actually this tautomerism occurs? As I said that hydrogen shifts from one place to another, actually it is not the same hydrogen that goes to that position. In this example I have shown here, say this is a ketone and it is being converted into enol form. It is this hydrogen which is labile. So, this hydrogen is actually taken by the solvent molecule. Solvent molecule forms a bond with this hydrogen. Now, this pair of electron that was being used to form bond between carbon and hydrogen shifts here and it forms a pi bond here. And then these pi electrons they shift to this atom, and now this atom captures one hydrogen from another solvent molecule. So, this remains in equilibrium. Some solvent molecules are losing their hydrogen and some are gaining their hydrogen, and ultimately they reach to an equilibrium. So, this keto form is converted into this enol form. So, remember this hydrogen may not be the same that has been lost from the same part of the molecule. Now, another special case that is the ring chain isomerism. This type of isomerism is shown by compounds which contain the ring as well as some carbon chain also. Let us see with the help of some examples. This compound, this is ethyl cyclopentane. Another example, methyl cyclohexane. This is 1,2-dimethyl cyclopentane. If we see the chain of carbon atom in these three molecules, what we find that all the three carbons, they contain 7 carbons and the chain is of 7 carbon, 1, 2, 3, 4, 5, 6 and 7, and it is the 7th carbon which is attached to 3rd carbon in this molecule. This is 1, 2, 3, 4, 5, 6 and 7, and it is the 7th carbon that is attached to 2nd carbon here, and in this molecule it is 1, 2, 3, 4, 5, 6, 7. It is the 6th carbon that is attached to 2nd carbon. So, the three compounds have the same chain of 7 carbons, but where do they differ? They differ that the chains have joined at different points to give a ring of different size. Now, where should we classify these compounds? These compounds are hydrocarbons, have no functional group, but the ring size is different as well as the chain size is also different, and they have a different substituents. This has one methyl substituent, this has one ethyl substituent, this has 2 methyl substituents, but molecular formula is same. So, such compounds are classified in a special group. We call them as a ring chain isomerism, when the compounds consist of same number of carbon atoms in the chain, but they form the chain and ring of different size. Now, let us move on to stereoisomerism. As I said that stereoisomerism is an important aspect of stereochemistry. Stereoisomerism arises when there is a difference in the arrangement of atoms in space, but their connectivity remains the same. That is, which atom is attached to which other atom, that remains the same. Stereoisomerism can further be of two types, configurational and conformational. And now, before going to this type of isomerism, let us try to understand what do you mean by the term configuration and conformation. These are two different terms which are very often used in stereochemistry. Configuration is the specific arrangement of atoms in space which characterizes a particular isomer. That is, one particular compound which has one particular type of connectivity of atoms, and the position of the atoms space is fixed, then that is called the configuration for that particular molecule. Conformation. Conformations are defined as the different arrangement of atoms which a molecule can acquire by rotation across single bond. For one particular configuration, we can have infinite number of conformations. Now, I would like to explain this thing with the help of models. Let us say this is a molecule in my hand. Now, in this, the carbon is attached to carbon and it has some different groups attached to it. Now, this is a configuration for this particular molecule. Now, this is one particular configuration for a molecule, but there is a free rotation possible across carbon-carbon single bond as well as this carbon and any other group which is present, a free rotation is there. Now, if this type of free rotation is there, it is not changing any configuration in the molecule. And similarly here, if we are rotating across this carbon-carbon single bond, what we find that a relative position of these groups is changing with respect to each other. Now, what happens? These relative arrangement of atoms, what we are getting by rotation across single bonds, they are called conformations. And as I told you that for one particular configuration, there can be a large number of conformation possible, because by a rotation of even a fraction of degree across this axis, we get a different conformation. So, from here two types of isomerism actually arise. One of them is called configurational isomerism and other conformational isomerism. First, we will take up the configurational isomerism. The configurational isomerism is itself of two types. They are called geometrical isomerism and optical isomerism. And now, the remaining part of our lecture now deal with mainly geometrical isomerism. Now, geometrical isomerism arises in the molecules due to restricted rotation between two atoms. Now, how the molecules can have restricted rotation? The restricted rotation the molecules can be due to the presence of a double bond or even single bond, but if the two atoms which we are considering, they are the part of the ring, and the compounds with the double bond, they might be having a carbon-carbon double bond or carbon-nitrogen double bond or nitrogen-nitrogen double bond or maybe some other atoms also. So, molecules which show a restricted rotation due to any of these reasons, they can show geometrical isomerism, because there is another condition also. So, all the compounds which have restricted rotation may not show geometrical isomerism. There are two conditions for a molecule to show geometrical isomerism. Let us discuss first that why this rotation around double bond is restricted. Now, this is one molecule in my hand where the two carbons are joined by double bond, and when I try to rotate it across this double bond, it is not possible. I find that there is a rigidity. Now, this rigidity, you may say that it is due to presence of these wires present here. How rigidity will be there in molecule? We can explain it on the basis of the structure of this carbon-carbon double bond, that how this rigidity arises. But first, let us see in the model that if there is a rigidity, no change is possible, and if these two carbons have groups, say red group represents some group, some portion of the molecule, there is a possibility that they may be on the same side or they may be present on the opposite side. Now, I cannot convert this molecule into this molecule or that molecule into this molecule, although they have similar groups. Both the compounds have two black groups, two red groups and two white groups. So, these are the compounds which are basically isomers. Will come again to this, that how this rigidity gives rise to this type of isomerism. Let us see the cause of this rigidity or this fixed structure in molecules with double bonds. This is the molecule showing single bond, there is a free rotation as I have shown before, and double bonds there is no rotation possible. This is actually the structure of alkene. Now, what happens here in alkenes? Each of the carbon is sp2 hybridized. After sp2 hybridization, the three orbitals which we get, they come in one plane. Say if it is simple ethylene, one bond is formed with one hydrogen here, another bond is formed with one hydrogen here, and third bond is formed with this carbon. So, these sp2 hybridized orbitals overlap on this axis between the two carbons, and on these axes with hydrogen if it is simple ethylene, or if it is some other alkene in presence of hydrogen, some other group will be there. But these 6 atoms, carbon, carbon and substituent on this and substituent on this, they come in one plane, which is shown here with the help of this gray board. This part of the molecule is in one plane. Now, the one p orbital of the carbon that has not taken part in hybridization, these p orbitals have their lobes above and below this plane. They are perpendicular to this plane. And now, these two p orbitals of the two carbons, they overlap sideways to form a pi bond between these two carbon atoms. So, in alkenes, there is one sigma bond present between these two carbon atoms, which is formed by the overlap of sp2 hybridized orbitals and one pi bond formed by the sideways overlap of these p orbitals. And it is this pi bond that does not allow the rotation across this axis, because now if we want to rotate the molecule across this axis, we must break this pi bond. That can be shown in the next slide. That if I want to rotate this carbon on this axis, what should happen? This overlapping must be abandoned, means this pi bond must break. Only then this p orbital will come in this plane, and now rotation has been possible across this axis. And breaking of this pi bond requires some energy, and this energy is approximately 270 kilojoule per mole for breaking this pi bond in simple ethylene. In other alkenes also the value is very near to it, and this much energy is not available at room temperature. So that is why free rotation is not possible. If we want to have the rotation across this carbon-carbon axis in compounds with having pi bond also, we must supply this much of energy so that these orbitals may rotate and then may overlap in the other direction, so that the position of these substituents may change. What happens actually, if you see in the energy level diagram, this is the molecule with the overlap p orbitals here, and this yellow group which is representing here the chlorine here basically is one isomer whose position is fixed. Now if I want to change the position of these two atoms, I must break this pi bond. For this energy is required to break the pi bond, and when energy is supplied, when it reaches here, it has the maximum energy when these orbitals are at 90 degree to each other and no overlapping is at that time, and then further rotation starts again the overlapping, a bond is again formed, but now the two atoms have changed their positions. So if we want to go from this molecule to this or from this molecule to this, we will have to supply the energy so that molecule passes through this high energy state or this transition state where no pi bond is there. And as I told you, this much of energy is not available at room temperature, so that is why these molecules acquire rigidity. They can be converted when we supply energy by some other source. Now how does this geometrical isomerism arise? One factor we have discussed, that there is a restricted rotation, and then second factor is that the two groups on these molecules, they should also be different. If these groups are not different, like this is the structure that is shown in the model. This represents the first structure here on the slide. Say this red group represents a methyl group. The two methyl groups are on the same site. So another molecule where two methyl groups are across, right? So these are now two different molecules because they cannot be interconverted by rotation. But suppose a molecule has got a similar group, like in this molecule, on one carbon there are two hydrogen atoms present. Even if we supply the energy, this carbon-carbon bond breaks, this carbon takes a rotation, so this hydrogen will take the place of this hydrogen and this hydrogen will come here. So we will get a similar molecule. So it means isomerism will not be possible. So there are two requirements for a molecule to show geometrical isomerism. One, that there should be restricted rotation, and second, the two atoms which are under consideration should have two different groups attached to them, right? Now let us again see this molecule. The same molecule 2-butene has been shown in different orientation only. This is one molecule when two methyl groups are present on the same site. There is another molecule when the two methyl groups are present on the opposite site. We have seen that these are representing two different molecules. Obviously, they will have different properties. But if I want to name them according to IUPAC system, I will number the carbon chain from one side, it is 1, 2, 3 and then 4. And this compound 1, 2, 3 and 4. So, both the compounds have a chain of 4 carbon atoms. The double bond is present in both the cases between carbon number 2 and 3. So, both the compounds should be named as 2-butene or butuene. Then how to differentiate? It means we must add something more to this IUPAC name so that we are able to differentiate these two isomers. And actually these two isomers what we are writing here, it is also called their configuration. So, we also call it as configurational nomenclature, means we want to name this configuration as well as this configuration and in such a way so that we are able to identify the two compounds. Earlier, two Latin words were used to name such compounds and they are cis and trans. Cis means on the same site, whereas trans means across. So, such isomers were named as cis or trans isomers, that if the similar groups or identical groups are on the same site, we will call that particular isomer as a cis isomer. And if the identical groups are across, as in this case, then such a isomer will be called as trans isomer. So, the full name for these compounds will be cis-2-butene and trans-2-butene. So, when we write the names like this, we can identify that about which configuration we are talking. Let us take another example. A similar type of example shown only with the help of model structure, that if there are similar groups, they may be any group, then if they are on the same site, isomer is cis, and if they are across, then they are trans. But suppose a molecule has got only one common group. These are the molecules where both the groups are common. If the molecule has got only one common group, then again we can name the compound by looking that particular common group, such as in this compound, it is 2,3-dichloroPent2ene. That is, a double bond is present between carbon number 2 and 3 and 2 chlorine atoms are present at carbon number 2 and 3. But the other groups, they become different. Now, this becomes a methyl group and this becomes a ethyl group. But we can name these isomers also as cis or trans by looking the relative position of one common group even. But I find here that 2 chlorine atoms are on the same site. So, this isomer is classified as cis, and here the 2 chlorine atoms are across, that is they are on the opposite side, we call this isomer as trans. Now, when there is no common group present, such as this compound. Now, this compound is meeting our both the requirements. There is a carbon-carbon double bond, so there is a restriction. Each of the carbon has 2 different groups, chlorine and bromine, here hydrogen and methyl, and 2 isomers are possible. But we cannot use this cis and trans system for naming these compounds. So, then for naming these compounds, another system is used in IUPAC, that is called EZ nomenclature. Again, the letters E and letter Z, they are derived from 2 German words. E stands for Entgegen and Z stands for Zusammen. And this nomenclature system was given by 3 scientists, R.S. Kahn, Sir Christopher Ingold and Vladimir Prelog. And the system is also called by taking the names of 3 scientists as Kahn, Ingold, Prelog system, or even further in short we call it as a CIP system of nomenclature. So, in CIP system of nomenclature, the geometrical isomers are designated as E are Z. Now, the naming of isomers by this system involves two steps. The first step is that the two groups which are attached to these carbon atoms or other atoms under consideration, that is, which are causing restricted rotation, we assign them some priorities, and these priorities are assigned by some rules which are called sequence rules. And the second step is that if the group getting the similar priority or the higher priority, they are on opposite side, then these isomers are called as E isomers. As I told before, E stands for a German word entgegen, which means opposite. And if groups getting the similar priority, they are or on the same side, such isomers are called as Z isomers. Z stands for another German word zusammen, and zusammen means together. So, let us see the sequence rules and apply it on different molecules for practice. The rule 1 says that look at the first atom attached to the alkene carbon, that is doubly bonded carbon atoms, and then atom with the higher atomic number precedes over the atom with lower atomic number, means the atom with higher atomic number is given a higher priority. Higher priority can also be numbered here, we sometimes call it as a first priority and second priority, but generally the term used is higher priority and lower priority. These are different atoms or groups which may be forming bond to the carbon, and their sequence order according to atomic number, as I said. Some groups are given here, such if iodine is present, it will be given a priority over bromine, bromine will be given priority over chlorine, then maybe if SH is linked to sulfur, then maybe fluorine, OH, NH2, CH3, H, and so on. And a lone pair of electron, if present somewhere, is given the least priority. So, first rule says that look for the atoms or the groups which are attached to this doubly bonded carbon and assign the priorities on the basis that group with a higher atomic number will be given the higher priority. Suppose there are some isotopes, that is on the same carbon one deuterium is attached and another hydrogen is attached. Then we use another part of this rule, and that part says that heavier isotope is given the higher priority. For example, if it is deuterium and hydrogen, that is protium, then deuterium will be given the higher priority. Suppose we have two isotopes of carbon, C13 and C12, then C13 being the higher isotope will be given the higher priority. Let us apply to some examples. This is an example that we were talking about where we cannot use cis or trans system, that is 1 bromo, 1 chloro, propene. Now, here we look at the first carbon, it has one hydrogen and one methyl group. Methyl is attached to carbon and here it is hydrogen. So, obviously, carbon of the methyl is given the higher priority. So, this is higher priority group, this is a lower priority group. We come on to this side, the two groups are chlorine and bromine. So, obviously, this bromine having higher atomic number gets a higher priority, chlorine gets a lower priority. So, what we find here, now the groups getting the higher priority, that is a similar property, they are on the same side. So, this isomer is Z isomer, zusammen. And in this isomer, the groups getting the higher priority, bromine and this methyl, they are across. So, this isomer is E isomer. Let us take another example. This is 1 bromo, 1 chloro, 2 fluoroethene. Here fluorine and hydrogen, fluorine gets the higher priority, hydrogen gets a lower priority, and on the other side chlorine gets a lower priority, this bromine gets a higher priority. So, what we find, the groups getting the higher priority, that is similar priority, are across. So, this isomer is E, and the name for compounds in this system are written E or Z before a small bracket before the name. So, it is written as E, 1 bromo, 1 chloro, 2 fluoroethene. Another example. Now, in this we have again no common group, but what we find, this is a methyl group here, this is a hydrogen, and out of the two, methyl gets a higher priority because it is attached through carbon. Here is the ethyl group and chlorine. This chlorine is given the higher priority because ethyl group is attached through carbon and chlorine has higher atomic number. So, what we find, the groups getting the higher priority are across. So, this isomer is assigned E configuration, and this isomer where this groups getting the higher priority, methyl and chlorine, they are on the same side, is assigned Z configuration. Now, in this case, now a problem comes. When I want to assign the priorities on this side, this is a methyl group and this is hydrogen. So, here I find carbon and here hydrogen. So, priorities assigned, higher priorities assigned to this group, methyl gets the higher priority. But how to assign priorities here? This is a methyl group, this is a ethyl group, and both are attached through carbon. So, our first rule cannot be applied at this stage, and in order to solve such problems, then a second rule was given. Second rule says that if the two substituents atom are same, or the two groups are attached through the similar atoms, then what we do? We look for the next atom in the chain, that is away from the double bond, and we compare the chain on the two atoms until we find a difference. Right? It will become clear when I will take up an example. And here precedence is decided at the first point of difference, means when we are moving across the two different chains, wherever we find the difference for the first time, that group is given the higher priority, where we find an atom of higher atomic number. Let us take this example. This is an isopropyl group, ethyl group, CH2 CH3, and this is a simple methyl group where we were held up in our previous example. So, what we find, that in this case, this carbon, which is the first carbon after the double bond, now has 3 atoms attached to it. One is carbon and 2 are hydrogens. It is CH2 and then 1 methyl. So, we get CHH at the second level, and in methyl there are all the 3 hydrogen atoms at the second level. So, we find the difference here. We find here a carbon and here a hydrogen. Carbon has the higher atomic number, so that is why ethyl group is given the priority over methyl group. So, we can use this in that same example, that ethyl is given the priority over methyl. Similarly, other groups like CH2Br will be given a priority over CH2NH2 because Br has a higher atomic number. CH2NH2 will be given the priority over CH3 because in this case we will meet nitrogen, and then this is given the priority over methyl group. So, this was the example where we were talking about. So, now we find that this ethyl is given the higher priority over this methyl, and we have the groups of higher priority across. So, this isomer will be assigned as E isomer. So, this configuration is E, and this compound is named as E3-methyl 2-pentene. Another example for these two groups, this is isopropyl group and this is CH2CH2OH group. Now, this group, if you go for the second position, first is carbon, second is 1 hydrogen, and at the next position I have 2 methyl groups. So, we meet 2 carbons. So, in this compound we have 2 carbon and 1 hydrogen at the second position. This is CH2, next is CH2. So, in this case at next position we have 2 hydrogen and 1 carbon. Although there is a hydroxyl group, but that does not come at the second position, and when we compare second position we find 2 carbon here and 1 carbon here. So, obviously this isopropyl group is given a higher priority over this group, although this is having hydroxyl group. Let us take another example. This is a tertiary butyl group and this is simple CH2OH group. When we look for the second positions, we find that in this case C, 2 hydrogens and then 1 oxygen. Whereas in this case after this carbon there are all the 3 carbon. So, here we get all 3 carbons, but here we get 1 oxygen and 2 hydrogen. So, we find here the oxygen atom of higher atomic number over the carbon. So that is why this smaller CH2 group, CH2OH group is given a higher priority over this tertiary butyl group. So our second rule can very easily solve this problem of assigning the priorities. Now let us take another example. In this case again we have a methyl here and hydrogen here. This methyl is attached through carbon and this methyl is given the higher priority. But here this carbon, which is an aldehyde group, has got oxygen joined by double bond one hydrogen, and in this case also CH2OH, this carbon is attached to hydrogen and one oxygen. How to decide the priorities? In such cases where some atoms are joined by a double bond or triple bond, then a third rule is used. And third rule says that where there is a double or triple bond, both the atoms are considered to be duplicated or triplicated as the case may be. So as in this case, this C double bond O, this will be considered as equivalent to one CO bond as it is present here. Next atom is oxygen, and then this oxygen is considered twice because it is attached to this carbon by double bond. So this is a second oxygen that we have written here in bracket. And similarly, this oxygen is attached to this carbon also by double bond. So this carbon is also to be duplicated, and we write a carbon attached to this oxygen here. These atoms which are written in brackets, they are the fictitious atoms. They are actually not present. We are writing them because we are duplicating these atoms. These atoms are sometimes also called as ghost atoms. So in our example now, this CHO, this will be considered equivalent to C, O, O and H, whereas CH2OH is equivalent to one oxygen and two hydrogens. So obviously we find a point of difference here, one more oxygen is this. So that is why this aldehyde group is given the higher priority over CH2OH group, and in this case now this is higher priority, the groups of higher priority are on the same side. So this isomer is assigned as Z isomer. Now there is one misconception. The misconception that comes, that students start comparing EZ with the cis-trans. These are altogether different systems, and there is no specific relationship between cis-trans or Z and E. As Z we are saying on the same side, cis also we are saying on the same side, but we are considering different things. In cis-trans system we are considering the identical groups, whereas in ZE system we are considering the groups with higher or similar priority, but they may be different groups. So they are based on different naming rules, so they should not be compared. Let us take with the help of one example. This is an example. This is 2-bromo 2-butene. Now if I consider it according to cis-trans system, the two methyl groups are on the same side. So this isomer is assigned cis configuration. But if I consider it according to priorities, then what happens? We find that bromine is given the higher priority over methyl in this case, but on this side methyl is given higher priority than hydrogen. So the group getting the higher priorities are across. So according to EZ system, this configuration is E. So never try to compare EZ with the cis-trans. They are altogether different systems. Now if a compound has got two double bonds, then how we will name such isomers according to EZ system? In this case, each double bond is separately assigned the configuration. As in this molecule, the configuration at the left hand double bond is E. How it is E? We see that this is chlorine and this hydrogen, so chlorine gets a higher priority, and on this carbon one hydrogen and one CH2 group. So this CH2 gets the higher priority. So groups getting the higher priority, CH2 and chlorine, they are across on this double bond. So this part is assigned E configuration. Now let us move on to this right part. What we find here, that there is one chlorine and one methyl. This chlorine is assigned higher priority over the methyl, and when we move on to this side, this is CH2 and this is H. So this CH2 is assigned a higher priority over H. So groups getting the higher priority are on the same side. So this double bond is assigned Z configuration. So when we write the name for this compound, we write like this, that according to IUPAC system, we number the carbons, we number the double bonds, and before those numbers we write their configuration, such as this compound is 1,5-dichloro-1,4-hexadiene, and this is carbon number 1. So double bond at 1 and 2 is assigned E configuration, and double bond at this 4 carbon is assigned Z configuration. So this is written as 1E 4Z 1,5-dichloro-1,4-hexadiene. Then we can have compounds where the double bond is not there, some other atoms are there, like carbon and nitrogen, that may be in case of oximes or maybe in case of azo compounds. We will take up these examples in our next lecture along with the optical isomerism. Thank you.
With this note, thank you so very much, sir. And I would like to tell all the viewers who are watching us right now that Dr. Arora would be with us tomorrow also, and I hope they might have got a deep insight into this very topic. And tomorrow also we are going to move forward, and as you said, optical isomerism we are going to cover. Thank you, sir. Thank you.